All right, hello and welcome everyone to a live class. Take two. Hope my in-person student is not getting too terribly bored over there, um, but maybe. Anywho, today we're going to be talking about the surface mine project, right? And we're just going to start from what I think is the beginning and just work our way through it. Number one on like the list of things to do, uh, access road, right? Um, there's an existing road here that's too steep. You can put your road anywhere you really want to, but I chose to start mine right here at the intersection with the main road, assuming we're going to be hauling our coal out that way. And I laid the road in approximately 6% grade all the way up to here. You can go up to 10, and without switchbacks, you can land over in this area somewhere. But I drew the road all the way up to here, and basically just stayed on grade because where I'm going to lay out my first cut is going to be right up on this point right here. So with that, there's a road in here, and the change in elevation is 280 feet to get from 1140 up to the 1420 bench level, right? The next thing we're going to do is consider our overburden volumes based on the parameters that were given for the project. So we've got, a seam thickness, slope, average slope of the reserves, and that sort of thing. And that's how we're going to calculate our amount of overburden, right? So the first thing we have to do is go over to our overburden and bench calculations, and we're going to calculate the maximum bench width, right? So we have our coal price per ton. We know our the rest of the information is given in the problem, probably, hopefully. So we're going to take that, and our maximum bench width for the Northern Reserve. Let's find out what it's going to be. So 1027 multiplied by coal price, that was $100 a ton, divided by the overburden removal cost in dollars per yard. I don't remember what that is. $5 per bank cubic yard. So we'll add that in. We'll multiply that by what? Coal thickness, 3 feet. Coal density, probably 80. Let's double check it because 80 pounds per cubic foot. I usually tend to go towards 80 instead of 85 because that's more likely a number you would see for metallurgical coal as opposed to, steam coal with a higher ash product, which weighs more. So multiply that by 80. That's the coal density. Wash recovery rate. We're assuming the surface mined coal isn't getting washed at all. So you're selling that raw. So that's 100%. And we'll just leave that. Then we're going to multiply that by the sine of 180, not 280, minus alpha and beta. It's our slope angle minus our high wall angle, which is 90 degrees. And our slope is, because I forget, 18 degrees in the north. So we're going to subtract the 18 degrees then 90 from that, and then we'll divide by whatever it says. Sine of 18 multiplied by the cosine of 0. $18 and multiply by the cosine of 0. All right, let's put our calculator and see what that gives us. I'm going to turn this into scientific mode. There we go. Yes, the cosine of 0 is 1, so we don't really have to worry about that. Let's do 180 minus 18 minus 90. Sine of that is 0.95. We're multiplying that by 80, the density, multiplied by 3, the mining height. It gives us 228.25. And then we're going to divide that by 18 sine. Probably. And that gets us 738. And then we're going to multiply that by 100. Divide by 5. 0.027. Even 02. It's so far gone. It's so far gone. What did we do? Maybe I take that one piece at a time and not screw it up so bad. So 0.027 multiplied by 100 divided by 5. 20. Multiply that by, make sure I got my math right here, 180 minus 90 minus 18. We'll take the sine of that, which is 0.95, and multiply that by 80. The density times the coal thickness, multiply by 3. 128.25. Oh, geez. And then we're going to divide that by and make sure to the right sine of 18. That's 0.3. So let's try that again. 228.25 multiplied by 0.3 or divided by 0.3. Oops. Okay, fine. $760. Multiply that by 20. Multiply that by 0.027. And we get a bench width that is 410 feet. Let's hope that's right. Probably. Okay, so our bench is 410 feet this direction. What's the associated high wall height? And that's just h tangent of the slope, right? Or h is equal to the tangent of the slope. Multiply the bench width. So the bench width is h inverse tangent of the slope. Okay, so we're going to take the whatever we just got, 410, and then we're going to multiply that by the tangent of 18. and that's 133 feet. It's more than I thought it was going to be. All right, so thanks to your classmate, we now have a better calculator that allows us to type everything in at one time, and I did it. And here it is. And so it was off by about 10 feet or so, probably some rounding error in there that I just knocked off. But so 399 feet, which is pretty wide, but this isn't that steep. And then to calculate our bench height, or bench height, I guess you could call it, but high wall height, we're solving for h again, and then it's the tangent of the slope angle multiplied by that bench width. So we have our final answer there from the last time. Sweet. And then we're going to multiply that by, multiply that by the tangent of 18 degrees. This is not my favorite calculator of all time, and why didn't they just do like reverse Polish notation instead?
Answer.
Oh, this is so Texas Instruments, but thank you. So we have a high wall height that says 130 feet. So yeah, you can, I guess, mind that if you want. Most likely, that would probably be, you'll probably limit it to be less than that, just because at some point you're going to need a safety bench, or it's going to need to be at an angle that's not 90 degrees, and about 100 feet is where that's at. So our high wall height is so pretty much 130 feet, but you're likely going to have to limit that to something more like 100 feet if it's going to be vertical. Like I said, you can put in a safety bench, put one at, I don't know, actually relatively low, and then you could probably take it, even more than that. But so for the purposes of this, though, we're going to limit that to 100 feet, and that's going to change. It's going to change our the bench width that we end up with, and we can go back into that as well. But for now, I'm going to go over to this map, and I've got this high wall that's sitting here that's 40 feet high, right? And so if we're going to use this arbitrary limit, this 100 feet, 68, that puts our new high wall at about right here, okay? Giving us 100 feet. Now, now you have to come in, you gotta have to decide what you're gonna do with this whole point here. You can mine the whole thing right off there. Mine the whole thing, and when you come back in to do your approximate, like, original contour, you can do, you can refill this back in. And also, though, you could, if you wanted to, leave the point here, shoot a box cut across it, and then, high wall mine this over in here, if you wanted to, and leave the rest of the bench the same. One, like, sort of advantage that might be is, it's less overburden removal. You're not going to have to try and put this point back on here, as an approximate original contour. So that's something, else that you would have to keep in mind if you were doing, like I said, this project in real life. But for the purposes of this project, I'm going to say that whole point goes, right? You just surface mine the whole thing. Now, so we need to go back, right, to this calculation, right? This h tangent of alpha beta, whichever one, that's alpha. And we can, if we want to use 100 feet instead, we can resolve for the bench width, right? So it's just h divided by the tangent of 40. I think I said inverse tangent earlier, but it's not. So if we take 100 feet with our newfangled calculator, I think we can just clear that for now, 100, and we divide that by the tangent of 18, we get bench width. It's like basically 308 feet on average. Okay, so let's write that down. I don't think I can like strike through or highlight that, but the bench width average is equal to whatever it was, 308 feet. And so that works for a big part of the property, right? Like you could take this this geometry, right? And as long as it looks kind of like this, you could just consider it the area of a triangle and the volume like we've calculated before, right? However, we've got this whole point coming off, right? The whole thing. So if we're going to take the whole thing off, we're going to need to calculate that volume, okay? Let's see if I can hatch this without doing anything else to it. I did. And I did it again. And we did it again. This little guy is just a tiny bit higher than, oh man, it went away. Let's do that one more time. And that little bit should go away too. But it won't hatch for some reason. Sure. Okay. Magic, right? So I just deleted that so the hatch would go in there. Now what we're going to do is this is going to give us at a minimum the area that we have. So we can just look at that. If we look at the properties, it'll give us the area in square feet. So yeah, let's just go ahead and do that now. We have it. 14104.73.5. So that's like 1.4 million square feet. If we multiply that by 3, it gives us what? About 4 million cubic feet of coal, right? So multiply that by 80. Oh, I did it wrong again. You had to push that by 80. Oh, that didn't. There we go. That's our pounds of coal. It's still there somehow. We've gone back to it. Okay. So there it is. Almost 170,000 tons that's left to be mined in the Northern Reserve. So I know we're talking about overburden calculations, but we've got that. We've got this part already calculated now. So Northern Reserve. $169,000. There are 56 tons, or 7 if you want to round up. Okay. And we're back for some more overburden calculations. Okay, so I'm going to calculate this using the volume feature or the volume calculation in AutoCAD, which is the one second measure geom command. And so I'm going to measure the volume of an object, which is this hatch. And then I have to specify like the height. So I'm going to use the average height for this because that's the best I can do in AutoCAD without using a different software package like Carlson or something like that. So let's multiply that by the average, which is 70 feet, right? 40 feet minimum here and 100 here. So the average is 70. And that gives us a volume of nearly 99 million cubic feet, right? And I also just found out in my lovely volume calculations that I neglected to convert cubic feet into cubic yards. So you'll notice these are pretty high, right? And it's because they're in cubic feet. And so I'll change that and update it and get that on the website as soon as I can. But here we are with 99 million cubic feet, which is approximately what? Let's get our calculator back out, wherever it went. Oh, there it is. Clear all of that. Let's get that 99 million, or well, we can even put in the whole thing if we want. 987,331 43.5. Sure, let's just do that. And then we'll divide that by 27 to get bank cubic yards. And so that leaves us with about 3.6 million, 3.7 million. Then we'll just say 3.66 million bank cubic yards there, right? Now, though, that's how much cubic yards we have. What I now need to do, we need to figure out how much space there's going to be here on this bench after we're done mining. And so we have to take into account both areas here in this case. So if we look at the properties, it'll give us the area. And so we can take that 104 for 73.5 plus we're going to add in this area as well. Oh, it might do both. Does it do both? No, area varies. Let's add in this one. 110, 252, 4.5. Sure. And so that gives about 2.5 million. And then we would do the same thing that we did in AutoCAD, just without the function within the program. We're just going to multiply that by the average height, which is 50 feet. And that gives us 125 and a half million cubic feet, right? So we'll have to take that answer and divide that by 27 to give us cubic yards, and we're at again about we're at about 4.6 million. So North Reserve storage. I shouldn't say storage, but let's just say fill capacity is approximately 4.65 million bank cubic yards. So your bank again. So we now have for the North Reserve a bench width, a bench height. Like you can see, like because of the this point out here like this, we see that our our average bench width of if we do that 100 feet high wall, our average bench width that's 300 feet or so, 308 feet it's an average, right? And it includes this big wide area. So it's all in there, but it's an average, right? And there we go. So we now know how much volume we have to remove. We know how much fill capacity we have, and we have an excess of about 1 million yards, right? Excess storage. Now these are bank cubic yards again. Remember that we'll be refilling them with loose yards, so we'll have to take into account the swell factor. But so far so good with this, right? So we've got the northern portion of the reserves. We know how much we have to remove. We know how much storage space there is in here, to get this back to grade. And we know our, surface recoverable reserves. We calculated based on that area, almost 170,000 tons, right? Now, we got to come over here to this other side, the southern side, do the same thing all over again, right? Going to do that all over again for that. And let's see if we can, remember our equations here. If we can, maybe. Let's pull that up. Here we go. Our bench width again is, okay, pull my calculator sort of back over here. That way, that it's up. Then we can type the whole thing in, 0.027 multiplied by 100 divided by 5, right? The $100 per ton and the $5 per bank cubic yard overburden removal. And then we'll multiply that by our coal thickness, which in the Southern Reserve is 4 feet, right? And we're going to multiply that by the coal density, 80 pounds per cubic foot. Yep. And we're going to add another parentheses in here because we're going to continue 4 times 80 times the sine of 180 minus 24 degrees minus 90. And then we need to close those parentheses and those and those. Okay. Back to here. Oh, wait. No, I'll close that one yet because we're going to divide by. Yeah, that's perfect. The sine of, I forget what it was again, 24 degrees multiplied by the cosine of, it's 0 again, because 90 minus 90 is 0. And that gives us average bench width of 388 feet. Okay, 388. Let's write that down. W sub B is equal to 388 feet. And if we remember, the height is then the tangent of the slope angle multiplied by the bench width, right? So let's take the tangent of 24 and then multiply that by our bench width, which was 388 feet. And once again, we get this like huge high wall height, right? It's $100 a ton coal is pretty good when you're selling it raw. So we're not going to be able to mine that. Like I said, it's too tall. Like I said, without a safety bench. So once again, I'm going to limit our high wall height to 100 feet. Then recalculate that average bench width by taking the height divided by the tangent of 24, height, which is 100 feet. Wait, what did I do? Oh, I need to divide that. That got me. 225 feet. And once again, back on the southern side, where nothing's been mined, there's our 100-foot sort of bench height. And then once again, this is what we're going to be mining. And there is a pretty large area over here, which has a low gap right here, and is the perfect location for a box cut if you would decide to put one in. The other thing that's going on over here is this, there's 30%, 31% of the coal still left in the ground where this deep mine is, right? And so when we go, we'll start calculating our our volume for this particular portion, of the coal. We have to consider that 69% of it's gone, right? And so we can do that calculation again if we pull this up, right? And for our maximum sort of bench width, given that, okay, no, that's not what I want to do. I want to well, just copy it. Let's copy it. I won't let me. There we go. And then to sort of take this into account, or 4, multiply that by 0.31, that's 1.24. Taking into account a recovery. That gives us 120-foot wide bench. And if we take that 120 and multiply it by the tangent of 24, we get 50 feet roughly, and so that cuts our high wall height and our bench width down pretty good. Um, I'm not saying don't mind this, but based on the economics, you're limited to a high wall height that's going to be a bench that's going to be less than this, right? So I can choose to mine it, but for here, this piece is going to have to be much, much smaller than the this. All right, it's going to be half that in this area. We'll get a mine. So what we're going to do next time is take this, right, and we're going to continue doing our hatch and volume calculations down here for the Southern Reserve, and then we'll get into the blasting calculation, calculating the production rate based on the high wall miner and that sort of stuff. See you then.